Welcome back to the last lecture on soft lithography. We get started with the advantages of soft lithography. So, now you have a fair deal of idea about both photolithography and soft lithography, and you are now in a position to understand what are the real advantages of both the techniques. Needless to say, even today for the microelectronic industry, photolithography is the technique. Industry still performs photolithography and all your silicon electronic devices. Photolithography, I think in my opinion, is going to be used for a long time. But there are, as you know, that there are lots of application areas which are emerging, which are coming up, where nano patterns, particularly with different types of polymers, are required, and soft lithography is very effectively catering to these segments. So, let us take a look into some of the advantages. So, it is convenient, inexpensive, it is accessible to non-experts. That is the most important thing. Sorry. You do not need to be a real expert in patterning to perform soft lithography. It might be very likely that you are a material scientist, you need some pattern surfaces, or you are a fluid mechanics specialist, you need some pattern surfaces to study behavior of a fluid on a hydrophobic surface. And in your lab with minimal facility, you can in fact create structures or templates that is necessary for you. That is one of the biggest advantage. Photolithography, unfortunately, you can't do that. You really need to have at least basic minimum facilities even to create some lines with let us say 5 micron line width or something like that. There are soft lithography processes are additive and therefore minimize the waste of materials, readily adaptable for rapid prototyping. Isotropic mechanical deformation of PDMS provides roots for complex patterns. This is something I really do not want to highlight, it is a bit of details. This is extremely important, no diffraction limitation, and this is wrong again, as low as 10 nanometer have been fabricated. We have already seen that structures down to 10 nanometers have been achieved. And non-planar surfaces, this is another major plus point of soft lithography, because most of the techniques rely a flexible stamp or a surface. You can create non-planar surfaces. You can also, we have seen that we can create 3-dimensional topographies. Good control over surface chemistry and very useful for interfacial engineering is extremely important. A very broad range of materials can be used, in contrast of photolithography, which unfortunately the direct patterning step is limited to photoresist only. This in fact goes on producing number of copies, indistinguishable copies at low cost, therefore, it is capable for rapid prototyping and applicable for large area patterning. So, the step and repeat processes that you need to do with photolithography, because to control exposure, because if you want to expose a large area by photolithography, there will be issues with the angle at which the UV exposure is falling. So, that can also be handled by soft lithography. So, you see soft lithography, as I mentioned, is a suite of techniques, polymer specific techniques, and it is really very helpful. Limitations. There are issues that, since in many cases you are making structures with an elastomer, particularly for replica molding and many other techniques, there might be issues like pairing. You have seen pairing, like two adjacent structures join up like this due to interaction again between them. There can be issues related to swelling, shrinking, etc. The people are still trying this. I always tell, I mean, take soft lithography as a technique for rapid prototyping of different type of polymers, then it fits perfectly. But the moment you start talking whether it can be integrated to the microelectronic industry, it becomes, it is a big question. From the standpoint of the techniques, yes, yes, it can be compatible. There are many techniques, maybe including nano imprinted lithography with etching. It can create structures that are compatible to the microelectronic industry. But whether technologically it can sustain the throughput that to which the industry is used to is a difficult question to ask, and I think it will take still some, it will still take some time before soft lithography based fabrication goes to the factory. Of course, the defect levels are higher because You can't achieve that level of control what you have in photolithography. This is important, and this you people should now understand that each of the techniques are sort of very specific. So, soft lithography as a whole is very wide, but many of the techniques are very specific and they have their limitation. For example, micro contact printing works on a limited range of surfaces. You just saw that you need to have the appropriate surface so that the silane can bind. Mimic is slow, not suitable for large area patterning. Replica molding, micro transfer molding, SAMIM, not micro transfer molding, they leave a sort of some sort of a remnant layer. So, there are issues, and more particularly micro transfer molding also works for only a specific class of let us say UV curable polymers. So, it is not each of the techniques. What I mean to say, or what I mean to highlight, that not all the techniques are very versatile. For example, some of the most versatile techniques are nano imperial lithography and capillary force lithography, which at least works for a wide range of polymers. Almost all glassy polymers can be handled by this particular method, these two methods. But assuming that NIL is pretty robust or CFL is pretty robust, and under appropriate condition you can implement them nicely for a large number of materials, or maybe replica molding with Silgard 184. Here is a major limitation of soft lithography. Soft lithography is a secondary patterning technique, as it can only produce a negative replica under appropriate condition, that too of a given stamp or a master. So, the moment you, let us say, would like to create patterns with two different geometric dimension, what is the essential requirement? You need structures which are, you need original stamps that are different. Without that you can't work, right. So, this is a major problem. So, if you would like to create structures like this, then you need a stamp which contains a negative replica of this particular pattern. If you need structures like this, or maybe here it is very interesting, they have the same periodicity, but the height of the structures are different, and you need different stamps, nothing can be done. So, this is one major limitation of soft lithography, and recently some I would say significant effort. So, that way what happens is the success of soft lithography depends on the availability of appropriate master. Which translates to the fact that for every different geometry of the patterns, geometry or for every different or every pattern, I will just reframe it, every pattern with different geometry, every pattern for creating a fresh stamp is required. That is a limitation. So, you see that there are no flexibility in modifying the morphology of the patterns. You have a stamp and the best what you can achieve is a negative replica, not more than that. Well, you can have some incomplete replications, let us say in CFL, and get a structure like this, but then controlling it in a reproducible manner is a big issue. You can still do that, but then again it gets limited, the periodicity, line width, etc., are determined by that of the stamp. So, significant amount of research is going on for the last few years in making soft lithography more flexible, not flexible in terms of like a Silgard stamp, but can you come up. So, the concepts are what is often called as beyond the master patterning. Patterning concept. What it means is that can you create structures that are not mere negative replicas. Why? Because this way every time you want to create a structure with a new geometry, new dimension, you need a original stamp, means that for executing soft lithography you are actually depending on a strong nanofab facility. You need that. It is not that. So, that in fact itself one of the major advantages, that it is executable by all and this and that, which is not the right case, because you need the appropriate stamp. To be honest, that is the fact. So, this is how what people have been looking at. This is particularly valid for places where you do not have a very good nanofabrication facility, but you have a stamp, and can you create structures which are different than only a mere replica. So, I will give you two examples now, and much later in the course when I teach you elastic contact instability, maybe the last topic I will cover, I will give you two more examples there, how these concepts, very recent developments are taking place in creating structures which are not limited to a mere negative replica of the original stamp. Here is the first example, which relies on the concept of miniaturization. So, you start something with something big, and then you lead to something that is small. You have seen an example of this while we were talking about the use of a reticle in projection lithography, but here this was pioneered by Professor Ashutosh Sharma at IIT Kanpur. What you see is it is very simple. Use a special type of a material called hydrogel. Hydrogel, again you can just search what it is. It is a special type of gel that contains lot of water, and what happens is, as the water evaporates, the size of the gel, it sort of shrinks. So, water evaporates, size shrinks, and Professor Sharma always emphasized that his idea was motivated by 90s blockbuster Hollywood movie Honey, I Shrunk the Kids. So, anyway what it does is, you do a simple imprinting like replica molding or whatever, but you imprint a block of hydrogel, and what it means, so it is a soft material, so you can create the structures and then let the gel block dry. So, as the gel block dries up, it shrinks in size, and as a consequence the patterns are present on the surface also shrink. So, you allow it to shrink up to certain level, then you simply replica mold another Silgard stamp from these shrunk gels. So, what have you done? You have started off with a bigger stamp, and then you have allowed the gel to shrink, and now you have created a stamp with smaller features, and then you can take another block of hydrogel and which you can emboss with this second generation stamp, run this shrinking process. So, it sort of operates in a loop, and you can achieve significant reduction. So, you can see here that you have a master pattern, you sort of do whatever we just showed you, imprint a block of gel, allow it to shrink, and then what you get is patterns which have much smaller periodicity. So, this is the first generation replica, this is the second generation replica, this is the third generation replica, and you can go down significantly for several cycles. Only problem is the shrinkage is isotropic, and therefore, there is a shrinkage which is advantage as well as a problem. There is shrinkage in periodicity as well as feature height, and if you do not start off with a stamp that has very high features, after 2-3 cycles the patterns simply tend to flatten out, but still the concept works, and this was one of the first examples where you can create structures which are smaller in lateral dimension, lateral size with a larger stamp. The second idea is this technique is referred to as the elastic recovery lithography. So, this is also a very nice concept. What you do is you take a stamp, let us say with periodicity lambda p, line width LP and height H0. So, now you understand that you can create a perfect negative replica by many of the soft lithography techniques. You can use nano imprinted lithography, you can use replica molding, you can use CFL. But the question to ask is, using this stamp, is it possible to create structures that have the same line width and periodicity, but have different feature height? Of course, the limitation is the feature height varies between 0 and H0. H0 is the height of the original stamp feature. What is the difference between this method and the previously reported method based on shrinkage? Here there is only reduction in the height, the periodicity does not change. So, you might be interested to do some combinatorial experiment, and this will be very, very useful. So, how do you do it? You in fact do it by using a concept that we have come across during replica molding. And what is replica molding? If you remember, when we talked about replica molding, we took seal guard. I mentioned clearly that seal guard initially, even when you mix the oligomer and the crosslink at the part A and part B, it is a pure liquid, it is in a liquid form. Then you anneal it for some duration, some 4 to 6 hours, it becomes an elastomeric solid. So, rheologically what is happening? This cross-linking process is actually transforming a purely viscous liquid to an elastic solid. And therefore, if you now look at the transients between these two stages, what is happening? This transition has to be through different levels of viscoelasticity, which one can clearly see if one does a rheometry during the transformation process. So, what it means that if you now take 2 seal guard blocks or films, none of them are fully cured, and it turns out that you actually do not need those 4 or 6 hours, roughly in 30 minutes a thin film fully crosslinks. However, if you pick up a film somewhere over here, let us say one is pre-cured for 10 minutes, one is pre-cured for 20 minutes, these two films have different levels of viscoelasticity. Obviously, the one that is pre-cured longer has higher level of elasticity as compared to the one which has been pre-cured for a shorter duration. And this is particularly what has been utilized in this is the particular idea that has been utilized in this concept. What you do is you take 2 identical seal guard 184 films, you sort of, I am again giving a very simplified picture, not going much into the details of what is happening. You pre-cure them for different durations. Let us say we have 2 films here, and one is let us say pre-cured for 10 minutes, one is let us say pre-cured for 20 minutes. So, what is the immediate thing you can tell? You can tell that this film has higher level of viscoelasticity as compared to this film. G dash is known as storage modulus. So, if you have done some course on complex fluids, you can immediately get an idea, but otherwise also you can find it out in the net, what is storage modulus, and this is loss modulus. So, these 2 parameters, or rather the relative values of these 2 parameters, give you an idea about the extent of the exact rheology of a viscoelastic material. So, what you do now? You emboss both the films with the same stamp. It is a weightless stamp for some reason which you will realize. You apply some force like nano imprint lithography and you achieve an intrinsic negative replica. But what you do is that what you must understand that you are embossing a viscoelastic film unlike a purely viscous film in nano imprint lithography. So, the energy you are spending, part of the energy is stored within the elastic matrix as elastic deformation energy. However, since the materials are viscoelastic, part of the energy is dissipated. So, next step is a very clever one which is not done in nano imprint lithography, and you withdraw the external force. So, what you now have? You have two embossed films or imprinted films, but there is no external force to sustain this deformation. You simply have taken it out. So, now the film tries to relax back to its original flat configuration, but the energy that has been consumed in deforming the film is not fully stored, because if you deform an elastic film and withdraw the load, that is exactly what happens when you stretch a rubber and just simply release the load, the rubber relaxes back to its original configuration. But this is not a pure elastomer, it is a viscoelastic material. So, it will recover or relax back due to stress relaxation, but only partly, and the extent of stress relaxation now becomes a function of the elasticity of the material. So, the film that has been pre-cured for a longer duration in fact relaxes more, and the film that is cured for a shorter duration relaxes less. So, what is the manifestation of this relaxation? The only manifestation of the relaxation is it will push up the stamp, and that is the reason you would like to use a very lightweight or almost a weightless stamp like a foil stamp or something like that, and you do that. Therefore, eventually what you will get, of course, you then subsequently place the films for subsequent cross linking to make the structures permanent, that is an important criteria, and simply what you get is simply by varying the pre-curing time. So, here you see you have these different pre-curing durations, you get structures with different feature height. You just look into this number here in the vertical scale bar. These are all atomic force microscope images, and therefore, it is extremely important for you to realize that I mean, since you are getting this height, then you can say that your technique has worked perfectly, but how do you get it? And this feature height, the vertical height, is something that only an AFM can give, no other microscope can give that to you. So, that in fact sort of paves us the way to take up atomic force microscopy very seriously, which we are going to do from the next class itself. No pre-curing, so that is a limiting case in fact. That means that the film is in a purely viscous stage, there is no elasticity and then there is no restoring effect, and therefore, the film fails to restore. So, with a stamp which has a depth of 120 nanometer, you get a perfect negative replica, which many times we refer to as a PNR, nothing to do with the railway PNR of course. You get a perfect negative replica, but see, you pre-cure for different durations and the times you need to control very carefully. So, essentially the viscoelasticity of the film during imprinting actually changes, and you get structures with different feature height. You can in fact get similar type of behavior with long chain molecules even in a glassy polymer, because of the fact that this is something I will avoid for the time being, because due to the entanglement effect there results in the entanglement of the long chain molecules even in a glassy polymer sort of results in some bit of viscoelasticity, and if you anneal such a film for a prolonged time, there is stress relaxation. So, you can sort of utilize that and can use this technique with a bit of variation in protocol for creating differential height structures even in a glassy polymer, but it works beautifully well for an elastomer. Of course, here you see that with roughly 27 minutes of pre-curing, the structure is nearly flat, only 7 nanometers. So, you cure it for even longer, you get completely flat films. That is another limiting case. So, this is one limiting case where the film, while it was patterned, was purely viscous, and on this side while the film was patterned, it was purely elastic. So, it results in a completely flat film, and the reason why this 27 or 30 is because what you see in the rheometer. So, see, after roughly 32 minutes the film sort of becomes fully cross-linked. So, it is purely elastic. How do you get that? G dash is roughly 2 orders higher than G double dash, and they do not change with time. So, if you do this experiment or run the rheometer longer, these two lines become parallel. Initially, you can see that G double dash is high compared to G dash, and therefore, the film is in a viscous state. This method has been very cleverly used to create topographic gradient surfaces. So, you have topographic patterns, but the height of the patterns sort of vary from one end to the other. So, when one talks about this pre-curing of the films, typically what one means is the films were put inside a oven to do the pre-curing. But instead of that, what was done was that you do the pre-curing on a hot plate. So, you take a hot plate, lab scale hot plate, and you keep the film upside down, film side is facing the hot plate. But what you do is that you take two blocks of different height and place the film in a slanted configuration. So, this part of the film is closer to the plate and this part of the film is further away from the plate. What it means is this part receives more heat flux as compared to this part for a definite duration of pre-curing, for any duration of pre-curing. And what does it mean? That this part, in fact, the Silgard over this part crosslinks more and this part crosslinks less, and intermediate areas exhibit intermediate levels of crosslinking. So, what does it mean? This way you can very easily create a film with a viscoelasticity gradient along its length. Now, do the same, repeat the same technique, and what now happens is different areas of the film exhibit different levels of stress relaxation. So, this part, let us mark this as part A or point A and this as B. This is A, so this has higher level of elasticity. So, this will undergo more stress relaxation. This is B, lower level of elasticity, this will undergo less level of stress relaxation. And as a consequence, here the stress relaxation is more, the feature height is less, here the feature height is more, and you can create topographic gradient surfaces. And most interestingly, you can vary the time duration of pre-curing, and you can control the steepness of the surface. So, all these can be done. So, these are some of the recent developments that are taking place, and with, let us say, biomimetic stamps or stamps with high feature height, this way you can in principle create structures which exhibit not only a topographic gradient, but a wettability gradient along its length. So, we talked about hydrophobic surface, hydrophilic surface. So, in principle it becomes possible to create structures that exhibits hydrophobic wetting state on one side and maybe hydrophilic wetting state on the other side. So, I stop here, and that is sort of the discussion I wanted to have on soft lithography. And next thing that I start in from the next lecture is a discussion on atomic force microscope, because all these characterizations we have been seeing are done by AFM, and let us say techniques like where you create features with different height, if you do not get an idea about the feature height, you do not even know whether your method works or not. So, that is why the utility of an AFM comes in. So, see you in an AFM class next. Thank you.